Right, question 24 is asking us first of all about structural isomers. So you have to explain what that means, but it says specifically by using those compounds. So you've got to make sure that you do relate it specifically to those. So the definition is that structural isomers have the same molecular formula and a different structural formula. So let's deal with the molecular formula first. Remember, that's just a list of how many atoms of each type, and you need to say what it is for these. So you need to say that all of them are C5H12. That's the molecular formula. And if you didn't write down the C5H12, you wouldn't get all the marks, because you're not then using these specific structures to emphasize the points. You've got to make sure you answer the question as asked. So they're all C5H12, but they have different structural formulae. Now what that means is that if you write them out, structural formula is when you write out the formula all on one line. So the top one, for example, would be CH3, CH2, 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 CH3. And the second one would be CH3, CH bracket CH3. Remember, the branch is written as a bracket, and then CH2, CH3. So these are different structural formulae. You've got to be precise about this term structural isomers. It's not enough to just say different structures, because if you take, for example, these two compounds, those have different structures, but they're not structural isomers, because if you wrote out the structural formula for those, it would be the same. Okay, so both of them are represented by that as a structural formula, because its structural formula doesn't show the arrangement in space. So you've got to be very careful with the words. Those are stereoisomers, which is something different, but we're concerned with structural isomers, which would be exemplified by these. Okay, so turning now to the boiling point question. The point is that the boiling point increases as the number of branches in the structure decreases, and that point needs to be clear. Okay, so the boiling point increases as the number of branches in the structure decreases. And the reason for that is that branching decreases the surface area available for contact with other molecules. It's not enough just to say surface area. You've got to explain why that matters. So branching decreases the surface area available for contact with other molecules, and therefore the more branches you have, the fewer induced dipole-dipole forces will be formed with other molecules. Okay, so those are the only type of intermolecular forces we've got here, because they're not polar molecules. So it's induced dipole-dipole forces, and the more branching you have, the smaller the surface area for contact, so the fewer induced dipole-dipole forces there will be between molecules, and therefore the less energy will be needed to break them. And you've got to get all those ideas in there. The kinds of intermolecular forces that you're talking about, the factors that affect how many of them there are or how strong they are, and relate that to the energy required to break them. That needs to be in there explicitly. And that's the explanation. Okay, part B, reactions of alkanes with halogens, UV light, that's radical substitution. You need to know that one. And then it asked you for the number of structural isomers you can get from this one and from this one when you get that substitution with chlorine. So the answer is, for this one, if it substitutes there, it's the same as if it substitutes there, because obviously those are both just the end of the molecule. If you just flip it over, it's the same thing. So those are not two different isomers. So that's one. Likewise, if you substitute it there, it's the same as if you substitute it there. Again, because of the symmetry, it doesn't matter which end of the chain you start from. If it's substituting at the second carbon, there's just one possibility. So that's the second possibility, and then there's this one, which is the unique third possibility. So the answer for that one is there are just three possibilities. With this one, it's less symmetrical, so this is one possibility. This is another one, if it substitutes at that position. This carbon, although it's got a branch, it's still got one hydrogen, so that one could also be substituted by chlorine. So that's a third possibility. But where you've got to be careful is that these two methyl groups are the same. Okay, they're both attached to the same carbon. So if you substituted a chlorine at either of them, you would get the same thing. And therefore, this one and this one only correspond to one additional possibility. So you've got 1, 2, 3, 4 possible isomers altogether. Okay, next thing then is that it wants to work out what compound we could have if it has an MR of that and was produced by substitution from that starting compound, which was compound A. So we can work that out by just using a sort of approximate calculation to tell us how many chlorines there need to be. So we've got 5 carbons in the structure, and we're going to have somewhere in the region of 10 hydrogens, because it's C5H12. So if we substitute, 1 or 2 or 3, it's going to be somewhere roughly 10 hydrogens. So 5 12s are 60 plus 10 gives us an MR of about 70. And so the difference between that and that must come from the chlorines. So we get 175 minus 70, 0.5 minus 70 is 105.5, which is roughly 3 times 35.5. So it looks like we've got 3 chlorines in the molecule. So that suggests that we've got C3, and it'll be H9 in fact, Cl3, because obviously if we had 12 hydrogens to start with, if we've put 3 chlorines in, we have to lose 3 hydrogens. So C3H9 Cl3, and then you just check that. 3 12s are 36 plus 9 is 45, plus 3 lots of 35.5 does indeed add up to 175.5. So that's the right molecular formula, and it asks for a possible structure. So it's obviously got to be based on that carbon skeleton, because that doesn't change during radical substitution, and you've just got to put 3 chlorines on anywhere you feel like. So we could put, for example, 2 there and 1 there, but any combination is fine so long as you don't exceed the number of bonds that are formed by any one carbon, so that would be fine. Okay, so question 25, we have to identify the products for these reactions. So the top one you hopefully recognise is dehydration of an alcohol, so elimination of water from an alcohol. So we're going to eliminate the OH group from here, and remember what then happens is you eliminate a hydrogen from the next door carbon, which is that one, and you form a double bond in between. So you're still going to have those 2 CH3 groups, like that. Then you're going to have a double bond across here, and you'll have the 2 hydrogens, like that. So you've just lost the OH from this hydrogen, the OH from this carbon and a hydrogen from that carbon, which gives you the water that was eliminated. So that's your product. These 2, you need to recognise that that's potassium dichromate, and that's an acid, so this is acidic potassium dichromate, and this is a primary alcohol, so this is the story that you can get 2 different oxidation products. If you distill, it removes the first oxidation product before it has a chance to oxidise any further. So this one gives you the product that's initially formed, which is the aldehyde, which looks like this. Okay, so you get that CHO group formed initially, but if you reflux, which means you keep on reacting for a long time, then the aldehyde gets oxidized further, and you get this, which is the carboxylic acid, which is drawn like that. So those are your other 2 products. When you're drawing these things, make sure that the bonds are connected up correctly. One of the things that loses people marks is when they write things like that, where the bond connects up to the hydrogen rather than the oxygen. So you've just got to be a little bit careful when you draw the structures. Make sure you get the right atoms connected up. Okay, part 2, it wants the systematic name of this alcohol. So what you do first is find the longest continuous chain, which is going to be 3 carbons. So that's prop. It's saturated, it's got no carbon-carbon double bond, so it's propan. That tells you it's saturated. And we're going to number the carbons from this end, because that way you have something to report already on carbon 1, whereas if you started from this end, nothing exciting happens till 2. And the rule is you want to keep that first number in the name as small as possible. So this is going to be carbon 1, 2 and 3. So 1 has the OH, so that's propan-1-ol. And carbon 2 has the branch, which is a methyl group, so it's 2-methyl propan-1-ol. Okay, part B is asking us for the mechanism of hydrolysis of this haloalkane with aqueous sodium hydroxide. The way it's written there is horrible. These all on one line structural formulae, you've got to work with them because they use them, as you've seen, quite a lot in the exam. But you need to try and avoid using them yourself because they're too crowded and messy. So the first thing I would do is redraw that in a more helpful format. So you could, for example, simply put some bonds in between, but I would be inclined to go for the skeletal formula because it's just so much simpler to see what's going on. So you just count 1, 2, 3, 4 carbons, bromines on the second one from that end, so that's your compound. So the mechanism, remember you're thinking curly arrows, you're thinking dipoles, you're thinking lone pairs. Those are always the 3 key features to take on board. So the starting point is that this is a polar molecule, so you've got to mark the dipole on there because that's what makes it vulnerable to attack. OH minus, the key feature it has to have shown is the lone pair on oxygen, because that's what it's going to use to mount its attack. And that's going to be attracted into the delta positive carbon, and you use a curly arrow to show that pair of electrons specifically being used to form a new bond. So something like that. Okay, it's got to be very precise. It can't just start vaguely over here somewhere, you know, something like that. That won't do, because it's not clear where that's coming from. So it's got to come specifically from the lone pair, and it's got to go right into that carbon to show that's what's being attacked. Now, obviously carbon can't have 5 bonds, so if it's going to accept this new bond coming in, it's got to let go of one of these electron pairs. And this pair is the one to go, because this can then just go out onto the bromine like that. Again, you've got to draw it precisely from the bond out onto the bromine atom. And that gives you this product. So you've now got the bond to OH instead, and the bromine has been released. But it's not just a bromine atom, because it's now got this pair of electrons all to itself. It's now a Br- ion. And so that's the other product. And that's the whole mechanism. It's a very simple mechanism. That's nucleophilic substitution. Okay, last question then is just asking us to look at the infrared spectrum and basically to say, well, what would change in the reaction to tell you that this compound which you started with, this is the bromoalkane, had gone, and that in its place you've got an alcohol group. So obviously the first thing is that this peak, which is the CBr peak, would disappear. In real life, you know, that's slightly problematic because this is in the fingerprint region. It's not always very obvious what's going on in that region. So generally speaking, you need to be careful of making deductions based on this region. But in this case, with a very specific question where it's told you this is the CBr peak, you can straightforwardly just simply say, right, that peak would have disappeared when the product is formed. The other thing, of course, is that you're replacing it with an OH peak. And so you're going to get an alcohol OH peak, and that comes down here. You don't have to draw it in, but that's what you would see appearing, which would tell you that the OH peak is formed. But what you do have to do is to quote your data sheet, and your data sheet tells you, if you look at it, that an alcohol OH peak is 3,200 to 3,600 wave numbers. So that's what you say, that a peak would appear. But give the wave number range, don't just say an alcohol OH peak. And that's it.